Welcome back. In the previous videos, we learned how to make alcohol from a compound containing a double bond, right? What if you want to take a single compound that contains one double bond and make a diol, okay? What's a diol? Means a compound containing two hydroxy groups, okay, placed adjacent to each other, okay. Okay, that is, let's say, I'm not going to draw you the actual compound. Let's say this side of the compound contains a chain, this side of the compound contains a chain, okay. But a diol is, just because you have two hydroxy compounds in the compound somewhere, that is not a diol, okay. They must be placed in group. These two hydroxy groups must be on two carbons adjacent to each other. This is what is known as a diol, okay. And there is only a certain way you can generate this, okay, and that is through formation of what is known as an epoxide. What is an epoxide? Again, some of these terms may be very, very unfamiliar for you, which is why I'm taking one step at a time, giving you the material slowly, rather than just giving them all at once, and you would be very much clueless at that point, all right? If your goal is a diol, okay, then you must go through an epoxide to get to a diol, okay? So this is the pathway, okay? So you go from a double bond to an epoxide, from an epoxide to a diol. But what is this epoxide, okay? An epoxide looks something like this. Now keep in mind, as I said, the diol is a very specific category of a compound where the two hydroxy groups are on two adjacent carbons, right? So the epoxide must be in some way that can assist formation of such a compound, all right? So an epoxide would look, again, this side might be attached to a ring, this side might be attached to a ring. An epoxide looks something like this, and I'm going to put the lone pair here, okay? At least for time being, until you can get used to it. So this is an epoxide, okay? Only if you can get your double bond into this form, then you'd be able to go to a diol, okay? So here's the general scheme of things, okay? Here is a compound containing, I'm not going to put anything in specific, okay? I'm just going to focus on the double bond, okay? So this is whatever is attached to this carbon, okay? You may be having multiple carbons or single carbons, it doesn't matter. But what I'm trying to focus here is, you're starting a compound containing a double bond, and your ultimate goal is you want a diol, that is two alcoholic or two hydroxy groups that are placed adjacent to each other, okay? This has to go through this epoxide form, okay? As I said, this could be attached to anything, okay? Okay, but it must go through this form. It's the epoxide, and epoxide is an intermediate, right? As I said, an intermediate is something that some reactions you'll be able to identify the intermediate because they have a longer half-life. Some of them, the intermediate is not observed because the reaction happens too fast. Okay, now this goes from epoxide, so this is your epoxide intermediate, and then that goes on to make your diol. Okay, now none of these other bonds in the chain are disturbed. It's only the epoxide is going to go on to make your diol. Okay, this is a general scheme of things. Okay, now we are going to look at two different reagents that can help you accomplish the formation of these epoxides. Okay, and that's what we're going to look at in the remainder of this video. All right, the first reagent is, it's called, in short, it's called MCPBA. Okay, it's known as, again, you don't have to memorize this, but it's a good thing if you remember. That makes you very unique, that you can remember something like this. It's called metachloroparabenzoic acid. Okay, now the word per means you have the maximum possible number of oxygen that can be attached to the compound. Okay, whenever you hear per, means the compound has possibly achieved its maximum number of oxygen count. Okay, it could be 2 could be maximum for that compound, it could be 3 could be maximum for that compound. You know, perchloric acid, if you remember from your general chemistry, you probably heard the term perchloric acid. Why is it called perchloric? Because the per indicates that this compound can only hold a maximum of 4, and this compound has achieved all 4 of them. And this is something you probably learned in your general chemistry class. Okay, whereas on the other hand, we don't use the word per for this one. Why? Because this compound can actually take 1 more oxygen, which is what leads to the perchloric acid. Chloric acid is a weak acid. Perchloric acid is a strong acid. Could you ask me, really, just 1 oxygen could make that much of a difference? You sure bet it can. All right, so chloric acid is a weak acid. Perchloric acid is an extremely, extremely strong acid. This is not weak as in what you would think of like a vinegar, but it is definitely weak compared to a perchloric acid, because the per indicates that the chlorine in this compound has achieved all 4 oxygen that it needs to get to the most strongest state possible. Okay, similarly, okay, I'm going to write you just, you know, metachlorobenzoic acid. Okay, then I can write you metachloroperbenzoic acid. Then you can tell it is very much similar to the difference between your perchloric acid and chloric acid. Okay, so we have not yet looked at acid functional groups, but I might take this as an opportunity to introduce to you. And don't worry about the meta, we haven't learned aromatic compounds yet, so that's why I keep holding on to this benzene thing for when we talk about aromatic compounds. Okay, so whenever you have this unique functional group, okay, I'm going to get a different color here and box it. Okay, this right here, you know, just like how we looked at OH being hydroxy, and a carbonyl group with just a hydrogen as an aldehyde, a carbonyl group sandwiched equally on both sides by 2 different groups that neither one of them is hydrogen, is a ketone. This right here is an acid. Okay, whether it's attached to a benzene ring or vinegar, which is this is vinegar, which is acetic acid. Anything with this is, so this right here, folks, is the metachlorobenzoic acid, right? This just has, this carbon can take actually 1 more oxygen without violating that 5-bond principle. Okay, so let's go ahead and write actually metachlorobenzoic acid. So this is metachlorobenzoic acid, which is similar to the chloric acid. And if you write metachlorobenzoic acid, the per has to be accounted for. So the chloro is still where it is. Everything looks the same, but if you notice, there's that extra oxygen. Okay, oxygen can only hold 2 bonds and carbon can only have 4 bonds. neither of those principles have been violated here. The carbon actually took one more oxygen in addition to the previous oxygen, but then this OH is not directly attached to the carbon now, but it is part of that acid group now. So this right here is the, let me get my pen, mark it. So this what gives it that per, okay, to the title. So metachloro, this is chloro, and this is perbenzoic acid. Okay, this whole thing is perbenzoic acid, and this is metachloro. Don't worry about the meta, we have not learned it. Okay, so if your goal, if your ultimate goal is to have a diol, then metachloroperbenzoic acid, and then we would also look at osmium tetroxide as the two potential reagents that can be used to achieve the job. All right, so let's go ahead and get our compound in. Okay, say if this is your compound, okay, say if this is your compound, right, and then you're going to react it with, I'm just going to write it as MCPBA. Okay, that's metachloroperbenzoic acid, and it reacts in dichloromethane. Okay, we've done the limonene synthesis, we've done clove oil synthesis, we've done cinnamaldehyde from cinnamon synthesis, right? In all three cases, we extracted that milky white liquid with a organic solvent. It smelled terrible to some of you, and that's nothing but this dichloromethane, okay, or also known as methylene chloride. Okay, this right here is also abbreviated as DCM, dichloromethane. Okay, this is a solvent, this is the actual reagent that we're going to react. Okay, I'm going to write the key intermediate that happens when you react this is, as I said, you got to go from the double bond to the epoxide formation. Okay. Oops. Okay. We can't have the double bond because the double bond what is converted to your epoxide, right? And this in turn gets converted to, keep in mind there is a hydrogen here, so we can write that here. Okay, and as I said, the epoxide chain is broken, and then you get the diol in adjacent carbons. Okay, so everything stays the same. A OH group goes here, another OH group goes here, and you get your hydrogen. So this is your diol, right? Now, for people that are over ambitious and do want to know what is the mechanism is and how this thing go about it, well, first this, okay, this compound reacts with MCPBA, okay, which is metachloroperbenzoic acid, and it results in the formation of an epoxide. Okay, things are quite easy at this point, and in fact the whole thing is not all that difficult. Okay, because the reaction is carried out, you know, there's, okay, so what do we ultimately want is, if there is water in the reaction medium, okay, okay, so because, you know, so that water reacts with H plus, okay, when water reacts with H plus, it makes hydronium ion, okay, and this reacts with hydronium ion. I'm going to write for time being as, okay, hydronium ion as this way, hydrogen H2O. Okay, what happens here is this lone pair reacts with the hydrogen, kicks the water out. Okay, so what that does then is, because the lone pair is now used as a bridge to connect the oxygen and the hydrogen, and in this process the double bond goes back to the water. So this is all pretty standard. You will see this probably multiple times. Okay, plus water. Why is the positive charge gone? Because, as I said, anytime a bond comes back, the positive and the bond is equal to a negative, neutralizes, so you end up with water. But this oxygen has lost a lone pair of electrons, so that's why it's got a positive charge. Okay, keep in mind there's still this hydrogen here. Okay. Now this, in turn, reacts with water again. Where does the water attack? Well, water again as lone pair of electrons, right? That again, this right here, this lone pair of electron attacks this carbon, very similar to either the mercury acetate or the bromonium ion formation. The bond gets moved back to the oxygen as a lone pair of electron. As I said, the bond comes in, the positive charge should disappear, but this is a complex reaction. Okay, so CH3, and then you got your OH, right? But what happened here is, in the process, this water has used this lone pair of electrons to make a bond, so that ends up having a positive charge again. Okay, this reacts with another water molecule where this hydrogen goes back to the water, and in the process, whenever I said the bond leaves, the positive charge also gets neutralized. You notice now that we have what we wanted, plus H3O plus. Okay, no matter how many times I would say this, until you actually make sense of what moving a certain arrow means, you will not be actually even able to comprehend some of these things. All right, so as you watch, try to make sense of what moving a particular arrow does, and if you have questions, please do ask me in class. But the overall rule of thumb, okay, for any chemical reaction, you have to know what is the overall rule of thumb for that reaction, and that is, whenever you react, whenever your goal is to have a diol formation, it means you got to use metachloroperbenzoic acid, and it reacts with a double bond, makes an epoxide. This right here is an epoxide, and then that in turn goes on to make your diol. So this is your product, right? All right, now there's one more reagent that you could use in place of your metachloroperbenzoic acid, and that is osmium tetroxide. Okay, so let's take the same exact compound that we looked at in the previous screen. Okay, and if you reacted with osmium tetroxide, and again, I'm going to use pyridine in this case. This is very similar to the dichloromethane that we use. Pyridine is primarily the solvent here. Okay, and osmium, see, this is a hydrocarbon, right? So it cannot be soluble in water. So most of the time, most organic reactions are carried out in organic solvents, unless your starting material can be dissolved in water, but at some point, either for extraction or some other purpose, you would be using some form of an organic solvent. And in this case, it's pyridine. Again, the osmium tetroxide has almost identical behavioral properties as does your metachloroperbenzoic acid. So you will have a diol formation. So I can write this hydrogen. So nothing gets disturbed, but you just had two hydroxy groups to it. So this is also another way to achieve. The mechanism is very similar. I don't want to go into it, but this is your product, which is very, very, very similar to what you had for your, and osmium is a very toxic chemical. So people usually prefer the metachloroperbenzoic acid method over the osmium tetroxide method. Even though it's very efficient, it is toxic, and osmium is very, very expensive to obtain. So both of these methods give you the same exact product, but one is much cheaper and probably relatively safe, and the other one is a little bit more expensive and toxic, but it's a little bit more efficient. Okay, so all you have to remember is the reagents. Okay, what happens when you add a specific reagent to an organic molecule is important. Okay, knowing the mechanism helps you understand the chemistry better, but some of you may not be able to remember everything on a test, but at least if you can remember the reagents and what its role in converting a reactant into a specific product, I think that should help you. All right, so I'm going to stop this video here. There's one more thing that I want to go over before we can call this week's a wrap. All right, so stay tuned.